Hi everyone. For 12.4, we're going to actually get started writing proofs. And that's what we've been working towards this whole module so far. We learned about if-then statements, which we're going to use. And we talked about how to link them together using the law of syllogism, which is really kind of the key to writing a proof. Now, before we actually write a proof, there's one last step to talk about. And that's providing a reason. So when you do a proof and you're linking together your if-then statements, every statement you make, you have to give a reason for it. That's part of the proof. Now, your reasons could be things like, number one, a definition. So an example would be, let's say I wanted to say, if an angle is a right angle, then it's 90 degrees. Now that's a true statement. Now my reason would be the definition of a right angle, because that is the definition of a right angle. So if your reason is like, just because that's what it is, then you say the definition. Your reason could also be all these different math rules we've learned so far and that we're going to keep learning throughout the semester. So for example, let's say I wanted to say if these two angles are vertical angles, then they are congruent. That would be the vertical angle theorem, and that would be my reason. So your reason can just be the name of the rule, the definition, postulate, theorem that let you know that it's true, or what you could do is give a very brief explanation. Sometimes you don't remember the actual name of the theorem or the postulate. If you just kind of briefly tell me what the reason is and it's right, I'll still give you credit for that. So go back to my example from just a second ago about vertical angles. Let's say you wanted to say, if these two angles are vertical angles, then you're congruent, or then they're congruent. And you couldn't remember the name of the theorem. If you just wrote, because vertical angles are congruent, I would still give you credit for that. You showed me that you knew what the theorem says, even if you didn't remember its name. So the quickest way to write a reason is to just tell me the name of the theorem. But if you can't remember it, you can always just give me an explanation. So that's what we're going to do today. Before we start writing proofs, we'll write proofs in this section, but on day 2. This is going to be a 2-day section. Today we're just going to practice writing reasons. And what I'm going to do, I'm going to go back to the very first thing we learned when we first started doing geometry, and that was points, lines, and planes. The very basics. And I'm going to start with 5 postulates about points, lines, and planes. And as a reminder, a postulate is like a theorem, it's a math rule, except where a theorem is usually like a more complex rule that's been proven. A postulate is more of a simple rule that may not have been proven, but we just accept it as true, and it's usually pretty obvious. So here's our first postulate. Through any 2 points is exactly one line. So what that means is if I drew 2 points here, maybe this is point P and this is point Q. And I said, how many lines go through both of those points? The answer is 1. If I draw a line that goes through those points, it is this line right here. And that's it. And when you say exactly 1, it's kind of saying 2 things. Number 1, it says there is 1. So if I draw 2 points, there's definitely a line that goes through them. But it's also saying there's no more than 1. There's not going to be 2 different lines that go through those same 2 points. And again, that's what I meant by postulate. Pretty simple. We don't need to prove that. It's kind of obvious. Okay, postulate number 2. Through any 3 non-collinear points. Now, collinear means on the same line. Non-collinear means not on the same line. So if I drew a 3rd point in this picture, but I made sure it wasn't on that same line, maybe I'll put point R over here. That's what we mean by 3 non-collinear points. 3 points that aren't perfectly lined up. Now through those goes exactly 1 plane. Now for this picture, the plane is my computer screen. The plane, the computer screen, contains all 3 points. Points P, R, and Q are all in the flat plane that you're looking at. There is no other plane, and remember when you're talking about planes, you're talking about 3-dimensional, like coming out towards you or angled or something like that. There's no other plane that would contain all 3 of those points. Okay, number 3, if 2 points lie in a plane, then the entire line containing those points is in that plane. So go back to my picture before I added R. Let's take R out of there. If we talk about the points P and Q, and the plane is my computer screen again, we say as long as P and Q are both in this plane that you're looking at, then the entire red line is also in that plane. And what that's kind of telling you is, like a line, a plane goes forever. That red line extends forever in two different directions, like this. But the plane extends forever in every direction, up, down, left, and right. So even though you may be looking at your computer screen and thinking it's only this big, the plane we're actually talking about extends beyond the computer screen. So just like that line goes forever in both directions, the plane goes forever in every direction. So that red line is contained entirely within the plane. Okay, number 4. If two lines intersect, then the intersection is one point. Intersect means cross, so if I draw a second line like this, crossing my first line, the intersection is that green point right there. Okay, that's another one that makes sense. If two lines cross, they make a point, exactly one point. So what it's saying is, if you have a line like this, and a second line crosses it, it can't cross it twice. This line is not going to cross it and then turn and cross it again, then it's not a straight line anymore, it's an angle. So a line can only cross another line once, is basically what it's saying. And then finally, if two lines intersect, the intersection, if two planes intersect, the intersection is exactly one line. And that's kind of like two lines crossing and make a point. So imagine if you had two pieces of paper and you hold them together, like one going this way and one going this way, and look at where those two pieces of paper touch, it's a perfect line going up and down. Or another good thing is look in the room you're sitting in. If you look up where a wall meets a ceiling, imagine the wall is one plane and the ceiling is the other plane. Well, that line going across where the line meets the wall, or where the wall meets the ceiling, that's the intersection. So whenever two planes meet, it makes a line. So what we're going to do, we're going to use those 5 postulates to practice our reasons. And I'm going to give you some true or false statements. We're going to decide if they're true or if they're false. And then we're going to explain our answer, probably for most of them using those postulates. So, question number 1 says there are 2 lines that go through points A and B. And I even named them for you, line AB and line BA. So I'll draw a picture to go with this. Here's point A and here's point B. And here is the line that goes through them. Now, a couple modules ago when we first started talking about this stuff, I said these are both good names for this line. I said you can call this line line AB or line BA, that's fine. But it doesn't mean it's 2 different lines. It means it's 2 different names for the same line. So this one's false. And in fact, it was postulate number 1 from our last page. If you go back to the last slide and look, number 1 said through any 2 lines, or through any 2 points, A and B, there is exactly one line. There can't be 2 different lines that go through those points. Okay. Number 2, the intersection of lines R and S is line T. Let's do a picture again. Here is line R, and remember, I told you guys, again, a couple modules ago when we first started talking about this stuff, one way to name a line is what we did up here, using 2 points, line AB or line BA. The other way is to just use a letter and put it next to the line like I did with the R there. So there's line R. Let's say this is line S. Their intersection is line T. Their intersection is this. So you're saying, is that a line? No, that's a point. So this one's going to be false again. And your reason would be one of our postulates again from the last slide. If 2 lines cross, their intersection is 1 point. It can't be a line. So you can see how we are using these postulates. These postulates are rules. We're saying they are 100% definite rules all the time, and we can use them in this case to show that these 2 statements are false. Let's do one more. This will be it for today. True or false again. This time I gave you the picture. I said true or false. One plane contains points A, B, and C in this picture below. So I have 3 points, A, B, and C. I can tell they're non-collinear because A and C are on that line, B is not. So these are 3 non-collinear points. So is there exactly one plane that contains those 3 points? Yeah, that was one of our postulates too. So I'm going to say true for this one. And the reason is straight out of our postulates. Through any 3 non-collinear points, that's what you're looking at, there is exactly one plane that contains them. So that's what you guys are going to do. This is just going back to point, line, and plane. We're going to keep it simple. We're not doing line segments yet. We're not doing angles yet, things like that. We're going back to points, lines, and planes, basic geometry. We learned a few postulates, and you guys are going to use them to practice providing reasons for statements.